We have discussed a lot on backtracking. Now let's start to solve problems based on backtracking. So the first one we're gonna work on is n queens problem. The problem is you will be given a board of n cross n size and you have to put n queens in this board in such a way that they don't attack each other. Interesting. For example, if we place the first queen here, and the second queen will be placed in such a way that it won't attack this first one. The first queen is at cell 00 and the other queen is at 1 2. So if you know the basic chess, the queen can move horizontally, that is in its right side, vertically in its left side, upside and downside, and it can move diagonally in all the four directions. But it can move one cell at a time. So these are the directions in which a queen can move. Keeping that in mind, let's see how we can solve this problem. We will be given n cross n matrix that is filled with values 0. What we need to do, we need to place n number of ones representing queen in non-attacking way. So to solve it, we need to think of four elements that we discussed in previous lecture. First is the choices. To place a queen in the board, we can either go row by row or we can go column by column. So here to place the queen 2, we have four choices. To place it in row 1 or in row 2 or in row 3 or in row 4. That's the case when we're going column by column. The other way can be you can place it in column 1 or column 2 or in column 3 or in column 4. These are the four choices we have for this queen. That's when we are going row by row. So these are the four choices when we are going row by row. That's up to you how you want to make these recursive calls. We're gonna go column by column. So the choices to put a queen in a column are four. Either we can put it in row 1 or in row 2 or in row 3 or in row 4. So these are the choices we have. Now coming to the second element is constraints. To validate if the current step is safe or not. So we'll check where we cannot place the queen. Basic constraints are if you have any queen present in horizontal, vertical or diagonal directions, you cannot place the queen at that cell. And as we will be going column by column, we don't need to check vertically. So we will validate if the cell is not facing the other queen horizontally and diagonally. So we cannot put it horizontally or diagonally. So the conditions will be like this. If we have any queen already placed to the left of this current queen, then we're gonna return false. We cannot place this queen there. And now we have to check diagonally. So if we are having any queen present diagonally to this current queen in the upper left portion, then we will return false. And similarly, if we have it in lower left portion, we are going to return false. In these two cases, when we are looking in upper left and the lower left, we are only looking if there is any queen placed diagonally to the current queen. And finally, if all these conditions return true, we can return true from is safe method because the queen can be placed at the current cell. Now the next element is recursion. When our choice is safe to be made, then we can make recursive calls to find the solution with the current choice. We saw the choices. For every column, we have rows as a choice to place the queen. We have 4 rows that represents 4 choices. Now what if the choices do not work out? Like here we can place the queen 1 here, and then we can place the queen 2 here in this column 2 at the third row. And now what about this queen 3? We don't have any row left to place this third queen, because if we place it in this column anywhere or in any row, it will be attacked by some other queen. So in this case, any of the choice is not working out. So we will go back and revert our decision for the cell, because putting the queen in the cell is not working out. So we will undo this decision by marking the cell with 0, and we will move on. This is called the backtracking step, where we undo the current decision and we go back to our previous step. First, we are going to place the queen at the current cell by marking it with 1, and then we are going to go column by column by making the recursive calls. So we're calling the save the queen method and passing column plus 1 to it. If this choice is going to work out, then this method is going to return true. Otherwise, if somewhere it does not work out, then it's going to go back to this execution, this current stack frame, and then we are going to execute the backtrack move. So here it will undo our decision to place the queen at the current cell. For doing this, it will mark back the current cell with 0 and will return false to say that this cell is not suitable to place the queen. Now the next and the last element, which is the goal. The goal or the objective is to place the queens at every column at the proper place so that they don't attack each other. And from there you get your base condition, which is basically to reach at the last column and place your last queen. When this is done, our goal is accomplished. Then we can stop the recursion, right? So the condition will be if the column index exceeds or crosses the last column index, then return true. The last column will be n minus 1, so we have to stop when it becomes n. So we have to stop right at n. So let's shape all this in single frame. What we will do, for every column, we're gonna go loop over the rows, which are the choices, and by putting a constraint check, we will see if the position where we're gonna place the queen is safe or not. If it is safe, we do make recursive calls for the next column, and if it is not safe, we will be out of the loop and go for different choice from the previous column, which is the backtracking move. And finally, when we will cross all the columns, that means we have reached to our goal. So this will be the base case. Let's start solving it. We will be given a 4x4 matrix filled up with zeros, and wherever we find the safe cell, we will update 1. Let's code the solution. Now let's analyze the complexity for n queens problem. For every column, we are traversing through n rows to check the possibility to place the queen. So the maximum branching factor is n, and the depth of the recursive calls will also be n. So the complexity will be n raised to power n, which is the upper bound. However, if we go deeper and see, the recursive call will happen for the remaining n queens only. Like after placing the first queen, we will be having n minus 1 options to place the others. So this recursive part is going to take n minus 1 time. And considering the isSafe call, that will run for n times for n columns, so the time complexity will be order of n square for this. And if we solve the equation, the recurrence relation, which is Tn equals to order of n square plus ntn minus 1, we gonna get Tn equals to On square On minus 2 factorial, which is approximately or almost equal to n factorial. So it is having order of n factorial complexity. That's pretty bad, but generally backtracking is used when we need to check all the possibilities to find a solution, right? Hence, it is expensive. Now, the space complexity. There will be n recursive calls at a time on the call stack, so complexity will be linear. Here you might think that for n cross n board it will require O n square space, but that isn't actually the part of algorithm. In algorithm complexity analysis, we analyze how much auxiliary space our algorithm will consume, and our algorithm isn't consuming any additional space. The board is already given to us, so we are not including it in the analysis. So the space complexity will be order of n.